Okay, so here's what we're going to. We're transitioning from talking about things in the force picture to talking about things in the energy picture. The energy picture has many advantages. First of all, it doesn't care if you have non-constant acceleration. It's a lot easier to work with because you're just computing some numbers. They're no vectors. The one thing we lose is time, but that's something we're willing to live with. So let me kind of start. Now this top line is all review, so that's why I started with it on the board here. In the force picture, everything are vectors. And because everything is vectors, that makes things complicated and annoying. And what we kind of try to do is just kind of cleave it into the two pieces of a vector, right? So on the top line for sizes, there's absolute value signs everywhere because we're just trying to get the amounts or sizes of those vectors. And then we're trying to we take care of directions separately entirely. I didn't bother to write them down here, but I'll just kind of talk through. This should all be review. So we can talk about direct interaction. That's Coulomb's law. The size of the force that the two charges will experience is given by this. And then the direction, of course, is that opposites attract and like repel. And you figure out a way to get that in your problem. And when you're working out, if two things are repelling like this, then you have to do the SOHCAHTOA or whatever you need to do to manage that direction in reality. Then we moved over to the intermediary picture where we can cleave apart cause and effect. So we can say that one charge causes an electric field, whether or not there's any other charges to react, and then the other charge reacts to that electric field and doesn't care what caused it. It's just reacting to the electric field's local conditions, right? Now, if you plug this in here, you get back Coulomb's law. It's just a convenient way to kind of talk about it as two separate pieces. And of course, along with this came a bunch of other direction rules as well, which basically, when put together, has to come up with the same thing as before, like charges repel and opposites attract. And the rules for that were that electric field lines point away from positive charges, and positive charges like to go downstream to other field lines. Negative charges make electric field lines radially toward them, and negative charges feel a force upstream to them. So if you put all that together, you'll just wind up with like repel and opposites attract. So that's the force picture, and of course homework number 1, you had to wrestle with all these vector directions, and it's, hopefully you're able to build off your physics 1 knowledge, but it's basically just a review in forces, right? So then we move over to energy. So energy, everything is just a number, it's a scalar. So there's no direction at all. Like kinetic energy doesn't have any direction. Potential energy doesn't have any direction. It's just a quantity or a number. Now one of the things that's going to potentially make this confusing is that these are just numbers. It's just a number. But these numbers can be plus or minus, okay? Just remember that when we say plus or minus here, it has a completely different meaning to what we were saying. Sometimes we call it force positive or negative, and what that means is it either points in the positive direction we call positive, or it points opposite that direction and we call it negative. So we normally use positive and negative for vectors as a proxy for vectors or vector components, right? Now, well before you ever heard of a vector, there were such things as positive and negative numbers, right? So when you have a negative balance in your bank account, it doesn't mean $100 to the left. It has a different meaning entirely, right? So remember, on this side, we are going to have plus or minus, but it has nothing to do with direction, okay? So let me kind of show you, kind of fill in the analysis boxes here. I'm going to give you the formula for potential energy. This is electric potential energy. I won't bother to normally write the electrical there, but I guess for the moment I will. So this means that just by bringing two charges near each other, they're going to have some stored up energy. And hopefully you don't have to be convinced, because if you bring two positive charges together, right, even though you might not see it, there's stored energy, because if I let them go, two positive charges are going to repel. They go faster and faster as they repel. The kinetic energy has to come from somewhere. Well, where did it come from? It came from the fact that it was stored when they were near each other. So let me give you the equation. Now this is something that I'm not able to prove for you without some calculus, so maybe you guys will do it in your supplement, your Physics 221. It's not that hard, but I don't think you can really do it without calculus. So we're going to just take it as a starting point for us. Okay? It is available on your equation sheet. You certainly don't have to memorize it. I want to point out a couple features. It looks similar to Coulomb's law, and it's easy to confuse them. One of the conspicuous things that is the feature is different is that the r in the denominator is not squared. Okay? It's just a single r. So that's one thing. And the other feature is that there's no absolute values. So in this equation, you can plug in the charges, sign and everything, and the equation will manage those signs for you. Okay? It's different from over here, where we wanted to absolute value these because we just wanted the size of this vector. We would worry about the direction completely separately. But this one, there is no other thing to append, right? This gives a number, and the number is all there is. So it's possible here to have both positive and negative potential energies. Now, negative potential energy is something that we have not looked at before. Usually, at least for me, I try to avoid it in Physics 1 because we have to save some fun for Physics 2. But let me mention, what does negative potential energy mean? We could have done it in Physics 1, and maybe that's where it might be more palatable to discuss with systems that you're more familiar and comfortable with. So let me take, for instance, gravitational potential energy, MGH. Does that ring a bell from Physics 1? That's the amount of energy you have stored because you're at some height above the ground, right? So we throw a ball up in the air, it goes up, it comes back down. And very typically, what we would do is we'd set h equals 0 at the lowest height of interest, right? In fact, that was the tip I gave you to specifically avoid potential energies that are negative, because then our potential energy is 0 there, but it's positive everywhere else, right? So on the way up, you're going to gain potential energy, right? You gain it because, of course, your height is increasing, right? So what has to give? Kinetic energy. So you lose kinetic energy, which means what happens in practice? The ball will slow down, right? So you gain kinetic energy, you lose, gain potentially lose kinetic energy. And at the top of the flight, assuming you throw it straight up, what's the kinetic energy at the very top? 0, because it's all in potential. But of course, it doesn't stay that way. Now that you've put that energy into storage, it's going to come right back out. That's one of the reasons why we can call it potential energy. Potential energy is stored energy. Stored energy means you can put it in storage, but then you can also go back and retrieve it from storage. So on the way down, what happens to the potential energy? It decreases, you lose potential energy, and what happens to the kinetic energy? You gain it back. And in fact, by the time you reach the same level that you threw it from, it'll be going just as fast, right? And the potential energy is back to 0. Now let me ask you this. What if you didn't know until you'd already set up your problem that there's a hole here? Is it going to go faster as it continue to go faster as it falls in the hole? Yeah. You're going to continue to gain kinetic energy, which means you have to get it from somewhere, so you have to lose potential energy. But what was your potential energy when you got to the level of the hole? It was 0. So where are you getting that new kinetic energy from? How do you lose from 0? So you have 0 potential energy here. So you have 0 energy in storage. Okay? Where are you getting this kinetic energy from?
Potential energy.
Potential energy. 0 is not the can't think of zero potential energy as the absence of any further stored energy. In this case, we can go to negative heights and negative potential energies, and negatives are lower than zero. Negative values are considered lower values. So if you lower your potential energy from 0 to a negative value, you can lose it, and therefore, of course, that's where you gain kinetic energy. So I could have thrown one of these in Physics 1 if I wanted to. I just tried to avoid it. So this construct that potential energy has to be 0 or more is not really realistic. If you go to negative values, that's just losing more than 0. And if you think of it this way, this is an arbitrary origin, right? I just decided where I set h equals 0. It's like setting an x equals 0. If I set x equals 0 right here, and I set x is positive this way, I can walk to positive x. Why wouldn't I be able to walk to negative x? What does it matter, right? It's just a reference point, x equals 0. That's the same way with potential energy. So 0 is just a reference. It's like an origin. There's nothing wrong with negative potential energies. Negative potential energies are just lower than 0. Okay? Does that make sense? So now in these systems, the negative potential energy thing is unavoidable. The equations basically have them baked in. And so in this case, yes, you could potentially, if you knew about the hole, you could set h equals 0 here at the bottom of the hole. And you could avoid negative potential energies again. But what I would say is that we can't, at some point, we have to be able to recognize that negative potential energies are okay. They're just lower values than 0. So what I'm going to do here is I'm going to draw what I'll call the potential energy spectrum. And in honor of gravity, which is our first experience with potential energy, I'm going to draw the arrow vertically like this. Because then it's just kind of nice, because higher on the board is more potential energy and lower on the board is less. Okay? The maximum value of potential energy that you can possibly have is plus infinity, right? That's the highest number you can have. In Physics 1, 0 is kind of the end of the line. That was the lowest height, at least of interest in every problem. But now we're learning that that is just a arbitrary distinction. In fact, the lowest amount of potential energy you can have is minus infinity. Okay? So this is kind of like our number line, including both positive and negative numbers that we'll refer back to. So if we're kind of, start to have a bunch of signs flying around and we're not exactly sure if something's increasing or decreasing, we'll just mark it off here, and then we'll see if it goes down on this line, it'll be a decrease. If it goes up on this line, it'll be an increase. So if something goes from, say, -5 to -10, that's a decrease. So going along with this, all systems seek lower potential energy. Okay? So if we leave a system and we think of its kind of natural tendency in how to evolve, it will always tend to move from a higher energy stored state to a lower one. Okay? And I should mention that it seeks the lowest potential energy available. So the lowest potential energy available. It doesn't mean that minus infinity is the lowest that every system has, because sometimes it's just not available. So whatever is the floor in that particular system, it wants to get down to it. Okay? Some systems, the floor might be a positive value. In many Physics 1 systems, we purposely set 0 to be the floor that is the lowest accessible. In some systems, the lowest available is negative, and they'll want to go to whatever that value is. And in some systems, even minus infinity will be available. So it goes to the lowest value it can. So that's just a general true thing about systems and how they evolve, is that they want to get that energy out of storage and manifest it. Now that's not to say that you can't temporarily reverse this. I can throw a ball up in the air just like I just did, and it'll go to higher potential energy, but that's just because, of course, you started it that way. Eventually, it's going to want to seek that lower potential energy. So you throw a ball up, what goes up must come down, right? Okay, are there any questions on that so far? All right, so I guess I'll leave that there for now. So this formula, you could certainly use it by itself, like Coulomb's law, but even on homework 1, you notice this progression that you kind of do the forces stuff first in the first half of the homework, and then you kind of graduate by the second half of the homework to the field picture, which is in many ways more handy, right? So since we already kind of understand that kind of intermediary thing, let's just go ahead and jump straight to cleaving this equation in half, okay? So let's talk about the cause, and let's talk about the effect, and cleave it in half. We cleave it in half pretty much the same way. On the effect side, it looks like this. It bears a striking resemblance, of course, to the previous effect equation. So remember how this worked. You had a property of space that was due to, of course, charges in the neighborhood. So a given location has an electric field, a given location has V, which is called voltage, okay? Okay. So V stands for voltage. I'll talk about that in just a second. So every point in space can be assigned a value. It doesn't mean that there's anything there yet, but it just, an empty location has a certain property. The electric field is the property that can be used to compute a force, should you choose to put something there. And the voltage is the property that, if you put something there, can be used to calculate the potential energy. So notice the same progression. You have a property of space. You put a charge there, and it'll tell you about that charge. So we have the property of the charge is the force that it feels or the potential energy that is stored. Right? So you can't have a force on nothing. You can't have potential energy of nothing. You have to put something there. Okay? So same deal. It's just the electric field is the property of space that helps you figure out the force on something placed there, and the voltage is the property of space that helps you figure out the potential energy should you choose to put something there. Okay? So the progression is very, very similar, right? Now before I move on to the cause side, let me just look at the units of this equation. The units of potential energy, or any energy, is what? Joules. And the units of charge are coulombs in SI. And so the units of voltage times voltage, we can figure out the units of voltage are joules per coulomb. Now, I guess I can compare and contrast that with the electric field units. That's newtons per coulomb. Okay? So, if the electric field tells you how many newtons of force are available at this location in space per coulomb that you put there, then the voltage tells you how many joules of potential energy are available at this location in space per coulomb that you put there, right? So one is the intermediary for force, one is the intermediary for energy. Now, the joule per coulomb actually gets a name. It's called a volt. So when you say 1 volt, what that means, if a location has 1 volt, It means it has 1 joule of potential energy available for every coulomb that you put there. Okay? So we will generally never write joules per coulomb just because it's more writing. We will abbreviate it to a volt. And that is where the quantity gets its nickname. It's called voltage in honor of the unit. So we can say the voltage is 10 volts, right? It's kind of confusing because voltage is the variable, and then the units are also volts, okay? It's kind of like if we decided to call mass kilogrammage, right? Okay, so instead of calling it mass, we called it by the units that we usually use. Of course, we don't do that. We don't call it kilogrammage. And I should mention that voltage also does have a more formal name. It's a very confusing name, and that's why I don't generally use it. So we kind of go with the nickname volts. The official name for voltage is called electric potential. Now that is the most confusing thing, perhaps, because that is not the same as electric potential energy. So there's electric potential energy, PE, and electric potential, which is volts, and they sound way too similar. So just to try to cause a distinction, I'll refer to electric potential more informally as voltage. Okay? Does that make sense? So that's the cause and effect, or sorry, that's the effect side. Basically, you put in at a location in space how many joules are available there per coulomb. You multiply it by how many coulombs you actually put there, and it'll tell you how many joules are available. Okay? Same deal. I guess let me finish up the cause side. Of course, the cause must be the rest of it. So the voltage itself must be KQ over R. So if you put in the voltage of one into the other, then you'll get back the potential energy law that I claimed was the case, right? So I'm going to spend some time today on both the cause and the effect, and one of the biggest things we have to do is make sure we understand what's going on with signs, okay? So the signs are no small matter. Are there any questions before I start off and kind of looking at the equations in more depth? Okay, so I'm going to start on the effect side. So let's just, this is an easier form to look at. P equals QV. I've already kind of told you the essence of what it is. You just take the voltage at a location, multiply it by the charge that you decide to put there, and it'll tell you the energy. So that's the essence of it. All I want to do now is make it more concrete by doing it with numbers and showing you how to manage the signs. Okay. Any questions before I clear some space? Okay, so let me clear some space here. So this is my equation that I want to really kind of get acquainted with. And since I'm just focusing in on the effect side, I'm going to not try to compute the voltage. I'm just going to say someone was nice enough to just give you the value. So let's say, for instance, that someone was nice enough to tell you at this location in space, there's 9 volts, plus 9 volts, and over here, plus 3 volts. Okay. Now, I haven't given you the voltage values everywhere in between. Let's assume there are no crazy surprises, okay? So just like I'm giving you 2 values of voltage, it's like giving you 2 different heights for a roller coaster. Let's say I have a roller coaster right here and here. There's lots of different ways that you could build this. You could just make it the most boring thing possible. You could do it like this. You could even do it like this. But let's not say we have something that's like this, because we don't know if we can get over that hump, right? So let's assume that we have 9 volts over here, 3 volts over here, but not 1,000,000 volts in between, because that's an issue, right? That might be a hill that you can't clear. So I'm assuming that you will have some kind of progression from here to here. It need not necessarily be a constant rate, because when we're moving into energy, we don't care about that. It's not necessary. So here's what I'm going to do. Let me come up with a charge, plus 1 coulomb. That's not a reasonable amount of charge. That's a lot of charge, but it's certainly a nice number to work with. And let me drop it at both locations. So I'm going to, in turn, not. So I'm going to drop it here, and I'm going to drop it here. That's not 2 charges. I'm going to try it out at both places in turn. And I want to get a sense of how much energy it has. So let's plug it in. So if I have a plus 1 coulomb charge, and I put it where there's 9 volts, what does that mean? It means 9 joules per coulomb. So if I multiply here, I get that it has 9 joules of energy when I'm placing it on the left there. Okay? So that's the amount of energy that is contained in that charge just by being where it is. Of course, that voltage is ultimately determined by other charges in the vicinity, but I'm not worried about it. That's the beauty of splitting it up into cause and effect. Let me try it at the other spot. Plus 1 coulomb placed at 3 volts. That's 3 joules per coulomb. That's plus 3 joules. All right. Which one of those is a larger value? Which one? 9, right? So this is larger, and this is smaller. And so since we know, this is why I left the potential energy spectrum up here, we know that systems seek the lowest potential energy available. So if we let this charge go from rest and didn't throw it, just like we could throw a ball up in the air and make it do something that it doesn't really want to do. But if we release it from rest, its natural progression would be to move from here to here, right? So let's call this the initial point, and call this the final point. I'm going to release the charge from rest here, and I'm going to ask what is its final speed when it arrives over here. So this positive charge has a natural progression to go from left to right. Question?
I would assume that's velocity.
Yes. So 2 different V's here. Capital V is voltage. Lowercase is speed. Lowercase v. So one of the things that I've discovered is that a positive charge, quote unquote, falls into lower voltage, right? Just like a ball tends to fall down, a positive charge falls into lower voltage, right? Because that's how it lowers its potential energy. Okay, so I can write that down here somewhere. A positive charge seeks lower voltage to get to lower potential energy. So a rock falls down under gravity to get to lower potential energy. A positive charge falls down into lower voltage to get to lower potential energy. Doesn't mean that you can't reverse it temporarily. You can, of course, throw a ball upward. It'll come back down. It doesn't mean you couldn't throw a positive charge into higher voltage, but it's going to fall back down into lower voltage. Positive charges seek lower voltage. Okay? If you want, we can draw these 2 values on the number line. The plus 9 is larger. Plus 3 is smaller. So it's no wonder that the system would want to progress downward, right? So let's do an example of a calculation. These kind of calculations there are a bunch of them in your homework too. We'll just go ahead and do an energy conservation. So since we have no non-conservative work, right? There's no friction or anything. This charge is just flying around in free space. It's like a ball falling with no air resistance or anything, or no friction. It's just going to convert out its potential energy into kinetic energy. So we just balance out KE plus PE. KE final, PE final. So all we're going to do here is simply say if you're losing potential energy, it's got to go into kinetic. And we can figure out, for instance, how fast it's going to go. Oh, I guess the one thing I also forgot I'm going to have to tell you is the mass of the charge, and I'm going to make it 1 kilogram. I must have been putting this together without a calculator. That's why everything's 1. Okay. Okay. So let's first go attack here. I guess let me remind you what the formula is for kinetic energy: 1/2 mv squared. And then I'm going to just kind of do it symbolically here before I just cram in the numbers. Be really careful about your uppercase v's and your lowercase v's. So lowercase v is speed and uppercase v is voltage. So that's what I have. Is that okay so far? All right, so now let's just go ahead and plug in the numbers. What's the initial kinetic energy? 0, because I dropped it at rest. And we already actually calculated that this here was plus 9 joules. And then we have 1/2 mv final squared plus, and then we calculated already that this is plus 3 joules. So by inspection, we can look at this and say, how much must this quantity be? 6 joules, right? We started off with 9 joules in storage and nothing in kinetic energy, but at the end we only have 3 joules in storage, so the 3 joules in storage had to come out to kinetic energy. So kinetic energy is 6 joules, right? And by the way, kinetic energy has to be positive, okay? So kinetic energy is not like potential energy. Kinetic energy has to be positive. Potential energy can be plus or minus. We've expanded that. We've just had a discussion about that. But kinetic energy, look at it, right? It's 1/2 mv squared. Okay? So there's nothing in there that could be negative. It's a representation of how much energy is in the motion. Mass is positive. Speed is positive already. Squared is definitely positive. Okay? So there's no way that that could come out to be negative. If you end up finding that you're trying to solve for 1/2 mv squared is minus 6 joules, you can't do anything with that. So don't just ignore that sign and just take the square root anyway, because there's something going wrong, okay? But in this case, we're fine, right? We have the kinetic energy 6 joules, and we can solve for the final speed. The final speed should be around 3.46 meters per second. So that's your energy progression, okay? Is that you're turning the stored energy into manifested kinetic energy, which of course comes with some associated speed. Again, it doesn't matter, just like in an energy problem, right? It doesn't matter if you went from here to here on a roller coaster, or went from here to here, the speed will still be the same at the end. It's set by the endpoints, right? It's set by the fact how much energy do you have at the beginning, how much energy you have at the end. It says nothing about the time, right? How long does this take? Obviously, if you had a roller coaster sliding down here and maybe going up the loop-de-loop, slowing down, it would take longer on the loop-de-loop, right? But we're not worried about time here. We want to know how fast does it arrive at the destination. Okay, are there any questions on that? Okay, so now we have to deal with the fact that there is also such a thing as minus charge, right? So let's switch out that the charge is now going to be minus. Let's see how that affects things. So this is now, what happens if this is minus 1 coulomb, okay? So now, going over here, I'm going to drop a minus charge instead. I'm going to drop it here. I'm going to drop it here. I'll do that first, just kind of like in turn, try it out each spot to get a sense of what is the potential energy at each point. So what would that change over here? Well, now there would be a minus sign in the charge, right? Not the voltage. The voltage is determined by some external means that who knows what determines it, but now it's a minus charge. That's minus, and so these are minus. So our potential energies are -9 and -3 joules, right? Which one is the larger one now? -3, that's right. And here, if we put them on the number line, we see that this little change makes a big difference. We put -3 and -9 joules on the number line. The lower potential energy is actually the -9. So it's actually reversed the desire of the charge, which, you know, hopefully isn't surprising, right? Whatever a plus charge wants to do, minus charge wants to do the opposite, right? So here, the natural progression would be initial and final. This charge would actually want to fall into higher voltage. And we can, of course, ask how fast is it going when it arrives. So if we go over here, we can write down that minus charges seek higher voltage, also in the service of getting to lower potential energy. So everything wants to get to lower energy, but how you achieve this feat is different. Positive charges achieve lower potential energy by falling into lower voltage, whereas minus charges achieve lower potential energy by falling into higher voltage. Okay? So the analogy I have for you here, everybody seeks lower potential energy. That's like everybody wants to be happy, right? I'm taking that as a universal thing, right? Everybody wants to be happy. Now, how you achieve happiness is a different story, okay? Some people, for instance, just like a positive charge seeks lower voltage, some people want to just give up all their worldly possessions and just go live on the beach, right? Okay, that is their idea of how to be happy, is to have less stuff. Some people think that the way to happiness is to be a billionaire, right? Get whatever stuff you need, right? Whatever you get more stuff, you'll be happier, right? So everyone has the same goal, but they can have completely opposite ideas of how to achieve that goal, either by going to lower voltage or higher voltage, okay? Does that make sense? Of course, we don't have this analogy in mass, right? There's only one kind of mass. So mass, all mass wants to fall down, right? A mass wants to fall down to get to the Earth. But if we had such a thing as negative mass, if we dropped it, it would fall up, right? We just don't have that. But we do have that with charge, right? We have charge of two types. Now this second statement, minus charges seek higher voltage to get to lower potential energy, this is where it really, the official name for voltage really starts to sound like very, starts to sound self-contradictory. Let me replace voltage with its official name, electric potential. Minus charges seek higher electric potential to get to lower electric potential energy. Okay? Let me repeat that. It just sounds like I contradicted myself. I didn't, because it's just that electric potential energy and electric potential sound so similar. Minus charges seek higher electric potential to get to lower electric potential energy. Okay? So you can see why I use voltage. Okay? Because if you're talking about a minus charge seeks higher voltage and lower potential energy, and there's nothing contradictory about that. Okay? Does that make sense? Sort of? Okay, well, maybe this will help. Let me go back to my equation. The computation looks very similar, right? I'm still going to balance out. Let's say I wanted to release this charge from rest over here, and I wanted to find out how fast it's going over here, right? So now we said that the progression would be that it actually starts at the, I forgot to mark it over here. This is now the smaller value. This is now the larger value. So it starts off at -3, and it ends up at -9. That is actually lowering. Now if you balanced off that equation, what is the kinetic energy? Minus 3 plus what equals what plus minus 9? What should this be? 6 or minus 6? It's 6. Still works. You haven't violated kinetic energy being negative. It can't be negative. Okay? So you'd still, it's the exact same thing. If it had the same mass, it would have the same final velocity. Whatever I said, whatever the final speed was before, it'll be that now. The only difference is that it moves from from right to left instead of the other way. Okay? So, I guess, are there any questions before I move forward on that? Okay, so remember when you're doing this, take the voltage at the location, multiply it by the charge. That will actually make a difference as to the sign of the potential energy. And then when you look at the potential energies, you have to decide which one is larger and which one's smaller. It's fine when they're positive, but when they're negative, you might want to use this number line because it's easy to accidentally forget. I mean, especially when you guys have been dealing with vectors so much, you've been accustomed to thinking of negative as just a filler for left or something, right? So you might be looking at these two numbers and think 9 is bigger than 3. But remember, negative 9 is smaller than minus 3, okay? Okay, so there's one more thing I want to point out about the scenario before I move on to the cause side. If I were, for instance, to solve this equation symbolically, which is, you know, always good practice, you could find the final speed is equal to, well, I'll just tell you what you would get. You get minus 2q delta v over m. And delta v, of course, delta anything is understood to be final minus initial, okay? Now that's not really that remarkable of an equation, but let me point out one feature of it, and this is something that you might not notice if you're cramming in the numbers right away. This is predicting the final speed of the charge. And it depends on the properties of the charge, its mass and the amount of charge. And then the only other thing that matters is delta V, which is the difference between the beginning and the end, right? What is the difference in voltage? So this is a difference. So let me point out something. If I were to go back to this scenario, I had 9 volts and 3 volts. If I made this 109 volts, and I made this 103 volts, would it affect any of my answers? No. The difference is still the same. Okay?
So the difference is positive or negative?
It depends, right? It's final minus initial. So if you are talking about the negative charge, the positive charge we started off with, it goes to lower voltage. So delta is negative, right? Indicating that it's decreasing. But in this charge, it's going to higher voltage. So the final is bigger than the initial, then it'd be positive, right? So I have it written down here, plus Q seeks lower voltage, that would indicate delta V is negative. A minus charge seeks higher voltage, that would indicate delta V is positive for those, right? I mean, this doesn't even have to be voltage, this is just a statement about deltas, right? When something decreases, delta is negative. When something increases, delta is positive, right?
So the delta V is always the final voltage minus the...
Delta anything, right? We use that in physics 1, first day, right? Delta x is x final minus x initial. That's the definition of delta, right? Delta is always final minus initial.
And that's how you can have a negative under the square root, but it always balances out because of the q.
Exactly. Right. So even though if you might be worried about the negative here, well, this could be negative and this could be negative, and it'll all work out perfectly fine. In fact, that's kind of what I was showing you here. I mean, it's just a manifestation of the fact that the kinetic energy itself will always come out to be positive. If not, you did something wrong. Because then if you, of course, solve for it, you will truly have a negative underneath here somewhere that something else doesn't get rid of. So this whole difference thing, this is something that we'll really lean on later, especially I think homework number 3. So not quite so much in homework 2, but in homework 3, it's all about delta. So in homework 2, you can kind of think of it like this. Homework 2 will be assigning specific voltage values to specific places. And just, you can talk about the difference in the 2 locations. You can certainly even recognize that the difference is all that matters. I think there are a few homework problems, not so many, but at least a few homework problems where they don't actually tell you the voltage over here is this and the voltage over here is this. It just tells you the difference, which is all that matters. But we really kind of get serious about that when we get to circuits in homework number 3. We almost never bother to say the voltage over here is this and the voltage over here is this. We almost exclusively say the voltage difference between these 2 places is this amount. In fact, when you guys get to lab, you'll have this thing called a voltmeter. The voltmeter does not have a single prong sticking out of it where you touch it and it tells you the voltage there. It has 2 prongs sticking out of it. And when you connect it, you connect one prong over here and one prong over here, and the readout is actually what is the difference in voltage between those 2 locations, which is really the only thing that matters. Okay? So don't get too hung up on that. In homework 2, which is the one you have currently on deck, it's perfectly permissible, and especially when you're kind of learning to walk on this stuff, to say the voltage over here is this and the voltage over here is this. But then later on, we'll recognize that the difference is the only important thing. And I wanted to show you that right now, just so you kind of know that it's coming later in much more seriousness. Okay, any questions on that before I move over to the cause side? Okay, so let's do that. So let's look at this equation. So this is the equation of a big Q making a voltage, of course, for maybe some other charges to respond to. But now we're just going to focus on the cause side. So let's do an example. Let's say my charge is plus 1 nanocoulomb. All right, this is an example. And let's say I want to calculate what's the voltage at 1 meter away and, I don't know, 3 meters away. Okay? So let's calculate the voltage at each of those locations. So I plug it into the formula. I was definitely doing this without a calculator. The reason I made it a nanocoulomb charge is because 10 to the minus 9 will perfectly kill the 10 to the 9 in the coulombs constant. Right? So I have just 9 times 1 over 1, so I can do that. And then here I have to divide by 3. If you don't believe me, you can plug it in your calculator. Okay, so let's see if we can draw that. So here's a plus charge. And we know that 1 meter away, a value, it's not a vector, it's just a number, is contributed. So 1 meter away, that's 1 meter here, this value of space gets a 9-volt value. Okay? You could say that about any 1 meter away. Okay? So in fact, what I might do is I might just draw myself a line to indicate that everywhere on this line, the value is 9 volts. That line is called an equipotential. An equipotential, just like it sounds, is a line along which you have equal potential, or potential being the more fancy name for voltage. And it's different from electric field because If you're talking about electric field, yes, if you're at a given location or a given distance away, the electric field size is the same, but because it's radial away, it changes direction, right? If this was a positive charge, the electric field over here would be like this, right, away. Over here would be like this, away. Same size, but now not this direction, this direction. And over here, it'd be away, same size, but away is this way, right? But this is not a vector being contributed, it's just a number. And so what we just do is we draw a dotted line to indicate that the number is the same, right? And we can draw another line, another equipotential, and we just label it once. Everywhere 3 meters away, there's a plus 3 volt value. I tried, nah, that's a terrible drawing. I was trying to draw those centered on the charge. I did not succeed. Well, hopefully you do a better job than me. So those are supposed to be circles centered on the charge. All right? Now, if these values are familiar, well, of course, these are exactly the voltage values I was using on the effect side, 9 volts and 3 volts, right? So we talked about a positive charge wanting to go to lower voltage, right? It would want to go from +9 to +3. Well, here we can understand that. That's just repulsion, right? It's just that positive charges repel. So now we're zooming out to the omniscient perspective where we're talking about charges just repelling and attracting. So rather than talking about them reacting to the local conditions of voltage, we can just simply see both charges and know why they're doing what they're doing. We talked about negative charges seeking higher voltage and wanting to go the other way. Well, we can just think of that as being that negative charge is attracted to the positive one, right? The positive BQ. So this is all coming down to like repel and opposites attract. First we cleaved it into a middleman with electric field, and now we're doing the same thing with energy, but it all has to come down to agreement, like repel and opposites attract. That make sense? Okay, so let me think of a way to, I can actually graph this voltage. There's a number of different ways to do that. The voltage goes from +9 to +3 to, and then eventually what happens when you go really far away? What happens to the voltage? 0, it goes to 0, right? So as R approaches infinity, the voltage approaches 0. So if I wanted to make a graph of this, one of the ways I can do it is like this. I can make a graph of what does the voltage look like versus radial distance. Where R is you're walking away in any direction, you'll see the voltage value decrease. It looks like this. And by the way, it is not linear because this is 1 over R function, right? So I kind of like to think of that as like a hill, okay? So just like a roller coaster or a slide might set up a hill, we think of other positive charges. So if this is the voltage created by big Q, then I like to think of positive charges as rolling off of it. Because positive charges, positive little q, seek lower voltage, right? Of course, we don't have this roller coasters like this, but there are such things as negative charges which seek higher voltage. So they would kind of roll up the voltage hill, okay? So that's one way to represent this. The other thing we might want to do is instead of just representing R is just generically walking away in any direction, we might actually want to put a number line here. So let's do that. I guess let me put the x equals 0 here. Oh, that's out. So put the x equals 0 here, because why not? I'll put the positive axis like this, and I'll put the negative axis like this. And we can kind of imagine our journey along this axis. Let's draw what that would look like. here's your voltage versus x. So here's the plus x, here's 0, here's minus x. So we go back here really far away in the minus x direction, and we have some kind of device that'll tell us the voltage there. Now if we're really far away over here, what's the voltage going to be? 0, right? That's what it is very far away. And then as we kind of walk along here, the voltage gets higher and higher and higher. At x equals 0, we apparently have put that where it's 9 volts. Let's keep up with the drawing here. Looks like this. This is plus 9 volts. And then, where the charge actually is now, what x value is the charge actually sitting on? I think it's plus 1 meter, right? So at plus 1 meter, what is our distance from the charge when we're at plus 1 meter? 0. So what happens to the voltage? It goes up, and what happens when you divide by 0? It goes infinity, yeah. So we have a voltage hill like this. It basically is like a hill. Really, it doesn't have any top. That was true over here, by the way, as well, right? There's no finite value that it tops out at. In fact, if you're right on the top of the charge, the voltage is infinity, plus infinity. All right? So then we start going further and further here. And what happens to the voltage now that we're going away from the charge? It starts to go back down until eventually it goes back to 0, right? So that looks like this. I tried to draw it symmetric, but I failed. Let me try again. That's marginally better. So that's my voltage hill. Okay? So think of it as like a positive charge creates this raised region of voltage values around it, peaking at where it's actually located, and of course getting smaller as you go further away, right? So if I were to drop a positive charge over on this side to react, it would seek lower voltage by repelling, right? Positive charge would go to the right to repel this positive charge, right? But what if I dropped the positive charge over here? Which way would it go? It would repel like this, because that's where the lower voltage is. So it kind of sniffs out, right? Where's that lower voltage? I want to get there. I want to fall down lower voltage. And in this case, if you're on this side of it, of course, you fall down this way. So this is why I talk about positive charges creating voltage hills, okay? So this is a quote-unquote voltage hill. I like to think of zero voltage as kind of like sea level, okay? That's the neutral. But positive charges create raised regions of positive voltage around them. Most pronounced right where they are, and then going back down to sea level when you get further away. So, let's go back to the cause and effect. The cause is V equals KQ over R. The positive charges create voltage hills. These are raised regions of positive voltage value. And so if positive charges create hills of raised voltage values, it's no wonder that other positive charges want to go to lower voltage to get off of those hills, because getting off those hills is getting away from other positive charges. So on the effect side, PE equals Q times V, we have that other positive charges seek lower voltage. They basically want to get away from the things that their other positive charges make. Okay? Minus charges seek higher voltage because they, of course, want to get on those hills, right? They want to get up those hills because that's attracting to opposite charge. So now we have left, obviously what we need to complete here, minus charges, and they're going to create what I'll call valleys. So if 0 voltage is like the baseline when there are no charges around, minus charges create a depression. They create a region that's a voltage that's lower, okay? So they create a ditch instead of a peak. Right? So let's take a look at that. What would that change in my equation? Well, if I made this negative, the only thing that would change is that the voltage values would come out negative, negative, negative. So still the R would go to infinity as you go to 0, or R would go to infinity, voltage would go to 0, but now instead of climbing off the hill, you're climbing out of the ditch, right? So now this would be negative 9, this would be negative 3, right? You may have seen this on maps before, right? If you want to represent that something is below sea level, you can also do contours, but you do contours of a different type so that you know that they're depressions instead of elevations, okay? So what does this look like? It just flips the whole thing upside down. So it just reverses, mirrors it, instead of everything that used to be positive voltage becomes negative. So as you walk away from a negative charge, you're climbing out of depression, out to V equals 0. Instead of down to V equals 0, you're going up to V equals 0. Again, if you chose instead, I guess I don't have room here, if you chose instead to represent it as an x-axis, it would be a depression that's centered where the charge is. And you climb out of it to either side.
So you had negative voltage there?
Yes, so these voltages are all going to be negative. Notice that the sign of Q is going to entirely control the sign of V, right? If Q is plus, then V has to be plus. There's no other way around it, right? R is a distance, so R can't be negative. If Q is negative, it's going to cause negative values all around it. So it creates negative values, and it bottoms out at minus infinity, but then when you go far away, it climbs out back out to 0. So think of it like 0, voltage being 0, that's kind of like nobody's around, that's kind of like your starting point. Positive charges build up from that, positive values are higher, and then negative charges create depressions where they depress the voltage value from 0. So it's like mountain peaks, positive charges are like mountains, and negative charges are like valleys. So we're basically thinking of this all as a landscape. And by the way, the analogy is not just an analogy, it's almost perfect. So I'm going to talk to you next time about how can we model this as contour maps. So this idea that positive charges create raised regions of voltage and negative charges create depression or lower values. And of course, the only way to go lower from 0 is to go negative. We should probably double check here. This is a negative charge here. Let me redraw it here just so that it kind of looks a little cleaner. So now we have a negative central charge. Nearby, it's more negative, so negative 9. And further away, it's less negative. You're climbing out of the ditch here, minus 3. We should probably double check that all is well on the effects side. So if we dropped for instance, a negative charge, it would repel. So it would go like that. Now we said that negative charges seek higher voltage. Is that the case here? Is the negative charge going to higher voltage? Yeah, it's climbing out of the ditch, right? It's going from a lower value, minus 9, to a higher value, minus 3. If we had a positive charge, it would of course attract. So a positive charge would go that way. Now we said that positive charge is like lower voltage. Is that going to lower voltage? Yes, it is. Okay? So everything is fine on the effect side. We're all good. Everything is all taking care of itself. And remember, ultimately, this comes down to like repel and opposites attract. There is nothing here that could contradict that. And it can't. We're just changing our models or our pictures. We're not changing the reality of the situation. Okay? So positive charges like to roll off of voltage hills because, of course, the charges they don't like, other positive charges make them. And positive charges also like to roll into valleys because what makes those valleys? Negative charges that they like. So positive charges are just like you might imagine a ball rolling around the landscape, right? A positive charge wants to roll off of a hillside, and if there's a ditch available, it will like to roll into that too. And then, of course, much harder to imagine negative charges. So negative charges like to roll up hills. They also like to climb out of valleys. They like to climb out of valleys because other negative charges make them. And they like to climb to the top of hills because those are made by charges they do like. Okay? So a lot of signs flying around. Potential energy can be positive or negative, and the potential energy can be due to a voltage, which also it can be positive or negative. Okay? So there's a lot of signs flying around. Okay? So you have to be comfortable with voltage being positive or negative, and then potential energy being positive or negative. Are there any questions on that? Okay, so what I want to do next, that is all the theory of how charges interact out on the table here. And all this cause-effect stuff, I just as a reminder, I did post a summary sheet for you so that this stuff is all kind of has a nice clean synopsis, and you can compare and contrast the force and electric field side with the potential energy and voltage side. Now let's take a look at how a calculation might proceed. I'm not going to have time to actually do the calculation today, probably, but I can at least give you a little bit of a roadmap as to how it works. Now let me compare the electric field picture with the voltage picture. So let's take a look at the electric field picture, something that's like your homework 1. So on homework 1 you might have had a plus Q1, plus Q2, plus Q3, or something like that. And of course, if I've labeled them as capital, so these are probably the cause of interest, right? And let's say I had a point P out here. So there's nothing there, and I was interested in finding out about what point P is like because of its neighborhood. So I would, of course, come up with a contribution from each of these three. So these are all positive, so the radially away, that's E1 would look something like this, E2 would look something like this, and E3 would look something like this. Right? I could calculate the net electric field at my point of interest, point P, by doing a vector addition of these three. Vector addition. That's where it gets really annoying. You have to do all your SOHCAHTOA and components and blah, 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 and it's tedious, right? And let's say, for instance, that you got, I don't know, that E net looks something like that. That's E net at point P, okay? Now, why would you be doing that? In some problems, that's the end, so, okay, what's the point of that? Well, probably the eventual point of it is that if you wanted to drop a charge there, let's say a positive charge, we know it's going to feel a force. Positive charges feel a force. I guess I should label that lowercase q, which is usually the effect charge that we care about the effect on. And we could calculate the force on it at that moment, right? And that's kind of it. So the problem is that as soon as it moves, the vector addition is going to change slightly. All the distances have changed, and the directions of the electric field contributions have changed, right? So while you might be able to say, initially we'll go off in this direction, you can't really trace the trajectory at all, right? You can't say, where does it go? Your electric field hockey applet can do it, because what it literally does is once it moves a little bit, it redoes the computation of what the electric field is there and redoes it every little time step. That's what computers are good at. Doing mindless calculations very fast, right? But we don't have that advantage. So we know already that the acceleration is not going to be constant, and so our ability to track this trajectory forward is very limited. And you'll notice that there is a conspicuous absence on homework 1 of these kind of problems. I don't ask you, well, what becomes of this thing once it gets shot off somewhere, right? Let's take a look at the voltage side. Same exact situation. I have 3 charges, Q1, Q2, and Q3. Same thing. So we're once again asked about some point out here, and we want to know about it. Well, this is why we moved to this picture. If you want to know the voltage at point P, you just add up V1 plus V2 plus V3. And that is just listing a string of numbers. So this is a scalar addition. It's the easiest thing in the world. Once you have those 3 numbers, there's no SOHCAHTOA involved, right? You just add up those contributions. Some of them might be positive and some of them might be negative, but that has nothing to do with vectors. It's just a string of positive and negative numbers. It's like when you balance your checkbook and you look at your deposits and withdrawals. So positive charges will contribute positive voltage values, and negative charges will contribute negative ones, but then you just add them up in a string, and that's it. It's very easy. Then, once you have that voltage, so you have the voltage at point P, and you drop a positive charge there, positive little q. Well, one of the things you won't quite be able to do with this approach, because it's scalars, is you won't be able to calculate the exact direction that it heads off of. That's one of the few advantages to the electric field approach, is it'll tell you which direction it'll initially shoot off at. But we do know that if you drop a positive charge and have 3 other positive charges, where is the eventual place that this is going to go to? Very far away, right? We don't know if it's going to head off in this direction, or this direction, or this direction. But we do know this. When it gets very far away from these charges, what is the voltage contributed by each one? 0. So the final voltage over here, very far away at infinity, is 0. So we could actually do the energy computation here very easily, just like we were doing before, right? KE plus PE. So here, let's say we let it go at rest. So the kinetic energy would be 0. The initial potential energy would be just the charge times the voltage here, right? And then, by the time it gets over here, it's lost the potential energy, loses potential energy, and it, of course, has gained as much kinetic energy as it can. And by the way, what is the potential energy here? If the voltage is 0, then what's the potential energy? 0. PE equals Q times V, so the potential energy will be 0. So this is a system where the floor happens to be here. So that particular system, 0 is the stopping point because that happens to be the lowest available, right? You can't get in this system, if all 3 charges are contributing positive values, there's no way that the voltage could get any lower than 0. So positive charges seeks lower voltage. The lowest voltage value available is 0. and happens to be the floor of this system. Now that's just a coincidence, because of course, in other systems, 0 might be the ceiling, and you can have access to negative potential energies. So you always have to look at what's available in the system. Sometimes 0 happens to be the floor, but in many systems it's not. And in fact, 0 can be the highest potential energy in some systems from which you can just only go down. Okay, so I'll do a calculation like this show you an example next time. So that's it for today.